Hi everyone, welcome to Mostly Math. Today we'll be talking about the proof of the following statement, that a square encloses the maximum area of all rectangles of a given perimeter. So in some way a square is the most efficient of all rectangles. Let's just go ahead and draw a rectangle so everyone knows what we're talking about. So we have a rectangle of sides x and y, and the condition of a given perimeter is going to be very important in this problem. So we're going to write this in the following form. It's going to be a perimeter of 2L, where L is some other length. And this gives us a condition of y in terms of x, which is useful. So we know that the sum of the distances has to be equal to the perimeter. Let's just go ahead and sum them. We have 2x's and 2y's. So 2x plus y is equal to 2L, or x plus y is equal to L. We can also write this in two equivalent ways. We can write x is equal to L minus y, or of course, y is equal to L minus x. Doesn't matter. So let's go ahead and, before we prove this using calculus, just find an intuitive explanation using this condition of why this statement should be true. We just want to get some numerical evidence under our belts before we whip out the derivatives. I mean, derivatives are cool, but they have to be motivated, right? Okay, great. So we had x plus y is equal to L up above. Write that in two forms. Now let's go ahead and let y indexed by n now to be equal to L over n for some n a positive integer, not including 0, of course, because it would blow up. So this tells us that x is now L minus y. Keep the n's here for clarity, which is equal to L minus L over n, L1 minus 1 over n, which can be rewritten as n minus 1 over n times L. Yep, sounds good. So now we have a rectangle labeled with sides L over n and n minus 1 over n L. Why have I chosen this? Well, I basically want to let n go to infinity, or this side go to 0, and see what happens to the total area. You see, as this side goes to 0, this side must increase, so it becomes even less squarical. So we'll find out what's wrong with not being square if we do this. We can immediately see that the area of the rectangle is just xn, yn is now equal to, well, we got xn over here, and minus 1 over n L, and we have yn up there, L over n, so the whole thing is now equal to n minus 1 over n squared L. And we can easily take the limit as n goes to infinity of this expression from elementary calculus. And as n goes to infinity, this expression, well, we can ignore the 1 here, so it just becomes n over n squared, which is just 1 over n. Oh, sorry, L squared. This is approximately L squared over n, which obviously goes as n goes to infinity to 0. So just with the integers indexing to infinity, we can certainly see that it's equal to 0. And we want to talk about the square case. Okay, it's going to be a square when xn equals yn. And this tells us, okay, so we have this expression equal to this one. The denominators are the same, and the L is the same as well. So the numerators have to be the same for them to be equal. It tells us that n minus 1 is equal to 1, or n equals 2. This is the square case, n equals 2. And great. Let's just go ahead and write down a few values and see what we can do here. We are going to write down a table of the following form. We have n over here, And we're going to have a over L squared over here. We're going to start with n equals 1. When we do this, we see that, sorry, this is a n, of course. We're going to be looking at this expression. 1 minus 1 is 0, so this is going to be 0. And geometrically, this corresponds to basically the worst possible rectangle, where you just take the two lengths and put them on top of each other. Pretty dumb. This is the worst rectangle. And we have n equals 2 now. Well, 2 minus 1 is 1 over 2 squared is 1/4, which is equal to 0.25, of course. And this is the square case. All sides have length L. And now let's do 3. 3 minus 1 is 2 over 3 squared is 9, 3/9. And this is, sorry, 2/9. I do apologize. 2/9. This is approximately 0.22. So we see it's worse than the square. And it looks a bit more rectangular. Look at 4. We get 4 minus 1 is 3 over 4 squared, which is 16. And this is about 0.19. Yep, it's getting worse, getting more rectangular. Talk about 5 now. 5 minus 1 is 4 over 25, which is approximately 0.16. And it's getting even more rectangular. We can continue this indefinitely to n equals infinity, where we'll have 0, and we'll have the two lengths on top of each other again. Worst possible rectangle. Great, so what does this tell us? Well, this tells us of all the integers, at least, the square is the best. But we don't know anything about in between the integers. And even if we did plot points here and found that it was worse, so what? We're not going to be able to plot all the possible points to see which one is the best. So we really need calculus to loop through all the points and tell us which one is the best. Great. Let's begin the real proof. That was just a numerical exercise so that we have an intuitive reason as to why we need calculus, and also why it really should be a square. That's the most efficient rectangle. All right. So recall previously we had a rectangle like so, sides x, y, and we found that y is equal to L minus x per our condition earlier. So now we can write down the area of the rectangle pretty easily. It's just x times L minus x, which we can rewrite as Lx minus x squared, because we're bound to take the derivative here. We're going to need two derivatives. So we compute a prime of x to be L minus 2x, and a double prime of x to be minus 2, which interestingly is the same for all values of x. Let's go ahead and draw a rudimentary plot of this function. So I'm going to stop at L, begin at 0, and it's a nice parabola, no problem. Just by the symmetry that we know about parabolas, we know it has a minimum somewhere, and it's going to be symmetric on either side. So by symmetry, the minimum has to be L over 2. But we want to use calculus to show this, number one, because calculus is easy, and number two, you might not graph it, and number three, you just have to do it. It's required. Okay, calculus. So to find the maximum and minimum, known collectively as the extremum, we first set the first derivative equal to 0, and then look at the second derivative to see if it's a minimum or maximum. So let's go ahead and do that. 0 is being set equal to a prime of x, which is L minus 2x, which immediately tells us that x is equal to L over 2, and also tells us that y is equal to L minus L over 2, which is L over 2 as well. So the answer popped out pretty straightforwardly. So we have x is equal to y, which is the definition of a square. So we've done it. In a sense, we've shown that it's an extremum. We could argue by geometry to show that it is a maximum, but we can also look at the second derivative using the second derivative test. So when we have a maximum, we'll be looking at the slopes to the left and the right of the maximum to find out if it is truly maximum. So if we really do have a maximum, it's going to be increasing before and decreasing after. Sorry, that's a minus, of course. Decreasing after. So we have d by dx going from positive to negative, or it's actually decreasing. Now, if the first derivative is decreasing, it means that the second derivative is actually less than 0. And we have to check that this is the case. It obviously is, since a double prime evaluated at the point in question, L over 2, is equal to minus 2. Therefore, it is indeed, well, celebrate, which is greater, less than 0, of course. It is indeed a maximum, and we are done. A square really is the most efficient rectangle in the sense that if someone gives you a length of fence 2L, I just chose 2L because it makes some of the constants easier. Otherwise, you'd have L over 4s lying around. Someone gives you a length of fence and you want to enclose the maximum area for some reason, you better use a square. Otherwise, you're going to use too much fence. And if you enjoyed this, want to see more, please subscribe. I'll see you next time.